Hello, statistics students. Today we're going to continue our study of conditional probability by looking at the addition rule. So let's get started on that. We need some more definitions. So we're going to say that two events A and B are mutually exclusive if they cannot happen at the same time. For instance, if event A, if you're rolling a die and event A is rolling an even number, and event B is rolling a 5. Those can't happen at the same time. They're mutually exclusive. A and B are not mutually exclusive if they can occur at the same time. For instance, rolling an even number and rolling a prime number. 2 is both even and prime. So rolling an even number and rolling a prime number are not mutually exclusive. Now, in a previous video, we learned the multiplication rule, and the multiplication rule was for the probability of A and B. Now we're going to learn the addition rule, which is for the probability of A or B. It is vital that you keep those separate. So when we say A or B mathematically, we mean A or B or both. So it could be here in A, could be in B or both. So in this figure, A or B would be anywhere inside this figure 8 shape, would be A or B or both. So it's the probability of A plus the probability of B minus the probability of the overlap. Why do we subtract the overlap? And we subtract it because it was counted twice. You can see here that this 1 is counted as part of A, because A isn't just this kind of Pac-Man shape over here to the left. A is this entire circle, and B is this entire circle. And if you do that, you count that one twice, so we have to take out one of those since it was double counted. So let's take a look at the probability of rolling an odd or a number less than 3. Here are our 3 odd numbers. Here are our 2 numbers less than 3. The number 1 is both, but you have these 2 numbers that are neither. That's why you have to show the entire sample space when you do these Venn diagrams. 4 and 6 are neither of these. So what's the probability of rolling an odd or less than 3? Well, one thing that you could do is just add up the number of items in the Venn diagram. 1, 2, 3, 4 out of 6. Done. Because as I said, A or B is anything within this kind of figure 8 shape. But if we use the formula, it's the probability of getting an odd number, which is not 2, but 3 out of 6. So we're counting that 1 there. And the probability of getting a less than 3 is not 1, but 2 out of 6. We've counted that 1 again. So now you have to subtract one of those overlaps, and you get the number that we came at just by looking at the picture. To kind of look at that as a, graphically, the probability of A is this kind of Pac-Man shape over here plus the overlap. The probability of B is this other Pac-Man shape plus the overlap. We have to take out one of those overlaps so that you get the area of all 3 of those regions, but that is the area inside the figure 8. Now, if you recall that we talked about in the multiplication rule, if A and B are independent, then the probability of B given A is just the probability of B, because A doesn't affect B at all. So there was kind of a simplification rule there if events were independent. There's a similar simplification rule if events are mutually exclusive. If there's no overlap, then the probability of A and B is 0. And this part just goes away. So if events are mutually exclusive, our addition rule simplifies. Now what you see here is on page 160 of our current textbook, some data on blood types in tabular format. So what is the probability that somebody has O positive blood if you choose at random? Well, O positive is 156. There are 409 people total. So the probability that somebody has O positive blood is 156 out of 409. You might think of it as, what is the probability of O and positive? Well, if we did that, it would be, that's an and, so we can use the multiplication rule. Be the probability of blood type O times the probability that somebody is Rh positive given that they have blood type O. Going back to that table, you can see this is the probability of blood type O. This is the probability of O, the conditional probability of positive given O, and we get exactly the same answer. Now you can't have blood type A and blood type B at the same time. So the probability of A and B is 0. There's no overlap between those two. But A or B, again, there's no overlap, so that probability is going to be 0. So you just take the probability of A and probability of B and add them together, because that's the addition rule for mutually exclusive events. Now, you should be able to look at the table and not just see where these numbers come from, but understand where these numbers come from. Given that somebody has type A, what is the probability that they have A positive? In other words, what is the probability that somebody is Rh positive given that they're type A? Go back to the table and confirm this. First thing you want to do is limit yourself to looking only at the type A blood type, folks, because that's what's given. Now, given that somebody is Rh positive, what is the probability of having type AB blood? Stop the video and figure that out on your own for a moment. So what is the probability that somebody has type AB given that they're Rh positive? There's your probability. All right, so blood types, blah, blah, blah. Let's get to something real. I have 80 people here. No, I got what? I'm 100 people? 40 and 32 is 72, 96 and 4 is 100. All right, I have 100 people here. How many of them like M&Ms? Answer to yourself. How many like M&Ms? The answer is not 24. The answer is 64, because this entire circle is the M&M circle. Now get the next one right. How many of them like Skittles? Had to pronounce it like a British person. All right, so it's not 32, it's 72 people like Skittles. So what is the probability that somebody likes M&Ms given that they like Skittles? Well, if we say given that they like Skittles, we're only looking at the Skittles circle. We are reducing our sample space to just these 72 people. Now, of these 72 people, these 40 also like M&Ms. So that's how we get 40 out of 72. And what's really interesting is that we could use Bayes' theorem to do the same thing. So if A is the event of liking M&Ms and B is the event of liking Skittles, then you should be able to come up with each of these probabilities. Look up the probability of A and you should get 64 out of 100. Make sure that you can get the probability of B given A. I'm not asking you to understand Bayes' theorem. I'm asking you to understand how to get each of these probabilities off of this picture. Then you can see that we end up with 40 out of 72, which is just what we got by looking at the picture. So maybe that gives you some confidence that Bayes' theorem is correct. And you'll notice that this probability down here is the overlap. And see if you can look at the picture and follow this as well. This probability is just this part of B. It's the ones who like Skittles but not M&Ms. This is the one that likes both. So this denominator is probability of B. It's the denominator is the total probability of people who like Skittles. And the numerator is just the overlap. Well, isn't that what we did by looking at the picture? The overlap divided by the total probability of Skittles? That's what Bayes' theorem is doing. All right, if all of this has been kind of, thrown at you pretty quickly, there's a great summary in our current textbook on page 161 about the multiplication rule and its simplification for independent events, and the addition rule and its simplification for mutually exclusive events. Here's an example. Let's let event A be rolling a prime number. So A over here consists of rolling a 2, a 3, or a 5. And let's let event B be rolling an even number. That's a 2, 4, or 6. What's the probability of A and B? You can tell by looking. There's 6 numbers total. There's only one of them that's both, so it's 1 out of 6. That's an A and B. That should be the multiplication rule. So it's the probability of A, which is 3 out of 6, times the probability of B given A. Well, if we're given A, we're only looking at those 3 numbers in the A circle, and the probability of B is just 1 out of 3. And you end up with 1 out of 6, just like you get from looking at the picture. Probability of A or B. A or B is anything within this figure 8 shape. 1, 2, 3, 4, 5 out of 6. Now that's an OR, so that should be the addition rule. So it's the probability of A, which is 3 out of 6, plus the probability of B, which is also 3 out of 6. Now you can't just stop there because that's 6 out of 6 or 1. And you can't say that there's a 100% chance of getting a prime or an even because there's still 1 out there. So you can see that we actually do have to subtract out the overlap to get, or one of the overlaps because it was counted twice, to get 5 out of 6. All right, that's it for this lesson. Have a great day.